In this set of notes, we are not actually going to be talking about the mean value theorem, but we will be talking about monotonicity. So our objective is to determine where a function is increasing and decreasing using the signs of derivatives. I would also like to focus on just what an increasing function looks like and a decreasing function looks like in general before we get to the derivative part. So in our first part here, it says increasing, decreasing behavior of functions. A function f of x is increasing on an interval a to b if, just write this down for now, f of x sub 2 is greater than f of x sub 1, where x2 is greater than x1. So that's basically saying that this x value later on in my function is going to be greater than an earlier output or an earlier x value's output. And then decreasing would be if f of x2 is smaller than the output of an earlier x value's output. And then monotonic is if it's just not increasing. So is it increasing or is it decreasing or staying the same and vice versa? A visual will probably give you more to go off of. So I'm just going to draw a random graph that has increasing and decreasing intervals. And then I'm going to show you a monotonic increasing function and a monotonic decreasing function. So this graph is increasing in this section, decreasing in this section, and then increasing after that. So basically my outputs, my later outputs are going to be bigger in the increasing section. And then my later outputs in my decreasing section should be smaller. Monotonic increasing is going to be where my outputs are going to be bigger or the same. So I might be moving along, take a pause for a moment, and then keep going. Right here, it looks like those outputs have not changed. Those outputs are the same for a moment. So that would be the non-increasing portion. Not increasing, not decreasing, just kind of staying the same there. And I said it just like how I visualize it. Basically, it's either increasing or taking a momentary pause or maybe a longer pause before going back down or before going back up. Monotonic decreasing, I'm going to draw something not so smooth. I'm going to draw a more elongated break than just a momentary one. So my function is going to be going down. And then I'm going to take a longer pause. All right, and then keep going back down. So this would be monotonic decreasing, either decreasing or not increasing for a moment, not decreasing, just staying where it's at for a little while. What I would like to do now is think about how we can get our increasing and decreasing behavior from derivatives though. So looking at this first graph, what is going on where we change from increasing to decreasing? Hopefully you said something along the lines of that the derivative is 0 there. What about strictly in my increasing section? What do the derivative values look like here? Positive. Decreasing section, the derivative values are negative. Not a coincidence. In fact, we've already talked about this once before, but we are formally going to be focusing on this a little bit more. So if I have an increasing function, that is going to be, or an increasing interval, that's where my derivative values are going to be positive. My decreasing intervals are where the derivatives are going to be negative. And then monotonic would be, with the equal to, because I could just be taking a break for a while where the derivative would be 0, or a momentary break where the derivative would be 0. So you just add the equal to part for the monotonic. Note. This means that a function cannot be increasing or decreasing where the derivative equals 0. Because it's not increasing, it's not decreasing, it's changing directions. And then we'd also want to consider where the derivative does not exist, because the derivative does not exist here. Although it's a turning point, it's not increasing, it's not decreasing, but its corner, the derivative doesn't exist there, it's not 0. So essentially, we're looking for critical points. Cannot be increasing or decreasing at critical points. And then we also can't be increasing or decreasing at values that aren't in the domain in the first place. If I have some sort of discontinuity, I can't be increasing or decreasing there because it doesn't exist on my graph in the first place. So we would say at X values not in the domain. Or you can say discontinuities, whatever you prefer, same thing. So our process for going through finding intervals where a function is increasing or decreasing is to first figure out your function's domain, because we don't want to find those critical points and then think that they're actually critical points, but they are not. So we're going to find the function's domain. That's going to help us with this part. Then we're going to find our critical points, which will help us with this part. And then we're going to set up a number line. So remember, the increasing or decreasing intervals depend on the derivative signs. So we'll set up a number line using the function's domain and the critical points, and then test values from each interval to get their derivative signs, whether they're positive or negative. So let's go ahead and do our first example. First and foremost, get that function's domain. This is a rational function, so we are going to have issues in the denominator. Denominator cannot equal 0. That is the only problem that we have here, so we're just going to say X cannot equal 0 is our domain. Now let's get our critical points. Which means we need to get our derivative. If you like using quotient rule, go for it. But personally, I would rather rewrite my function as X to the -2. And then I can go back into the rational form if you like. I probably will. So the derivative of our function is going to be -2 X to the -3. If I rewrite that, the X is the part with the negative exponent. So just the X to the -3 would go down to the denominator as X to the +3. All right, so now to find those critical points, remember that's going to occur where your derivative equals 0 and where the derivative does not exist. All right, so go ahead and figure out if it equals 0 anywhere and if it does not exist anywhere. So this will actually never equal 0. I have a constant in my numerator. I have a variable in my denominator. If my denominator ever equals 0, that's a problem. So this will never actually equal 0, so there's no solutions from here. Moving on to where the derivative does not exist. Kind of just talked about it. I can't have division by 0 here, so X cannot equal or where x equals 0 is going to cause me to have a problem in my derivative. But remember, we need to check to see if these are in the domain in the first place. X equals 0 is literally not in our domain, so this is not a critical point. So we don't have any critical points from this function, actually, and that's okay. Because remember, we test not just critical points, but we also test the discontinuities from our function, which we have one, we have 0. So I'm going to do that third step and create our number line, our f prime number line. Okay, so normally it would be critical points and any discontinuities from our domain. We only have discontinuities from our domain, no critical points. So only putting the 0 on there. I'm going to test numbers from each interval, which it looks like we have 2 in our derivative. So let's try -1. I'll erase my calculations when I'm done. -1 cubed is still -1. I get 2 as a result, which is a positive number. And I'm writing positive, not the number itself, because it's the signs of the derivatives that tell me if it's increasing or decreasing. Go ahead and pick a number from the right side. Get the sign. I'm going to do +1. Get -2/1, which is a negative number. So we can go ahead and write up our increasing and decreasing intervals now that we know the signs. My function is increasing from -∞ to 0 and decreasing from 0 to infinity. Look into the future, we will actually be using a lot of the things that we've been learning about, like critical points, increasing and decreasing. There's going to be some more things that we learn about in the next set of notes that are going to help us sketch graphs using calculus ideas versus when you were back in Algebra 2 learning about like vertex and other things. So this is going to be something that helps us sketch graphs later on. Moving on to question 3. Show that f of x equals -½ x cubed plus x squared minus x is a monotonic decreasing function. First and foremost, decreasing functions are where the derivative values are negative. And then monotonic means that it could also be staying still for a little while, so that's the equal to part. In order to do that, we want to still go through that same process of figuring out the intervals. So we'll start off with finding our domain. So we'll have to find our critical points. So the domain of this function would be all real numbers because it's a polynomial. So I'm not going to have any discontinuities on my number line that I write up for the decreasing intervals. Now we're going to go ahead and find our critical points, which means we'll need the derivative. Derivative of our first term would be -3/2 x cubed, or I'm sorry, x squared. Next term, the derivative would be 2x. And then last term derivative, -1. Remember, critical points occur where derivative equals 0 and where the derivative does not exist. So I'm going to go ahead and set my derivative function equal to 0. And I personally want to try to see if I can factor this. And I don't like having that fractional leading coefficient. So what I'm gonna do is multiply by the denominator that I don't want. So I'm gonna multiply everything by 2, especially since I have an equation here. I can go ahead and do that. And we get negative 3x squared plus 4x minus 2 still equals 0. So I'm going to play around with that and see if I can factor it. I want you to try as well. And worst comes to worst, if we can't figure out nice factors, we could use the quadratic formula. All right, I have tried playing around with this. I cannot come up with good combinations, so I think we will have to use the quadratic formula. Opposite b plus or minus square root of b squared minus 4 times a times c all over 2a. On the inside, we have 16. Negative 4 times negative 3 is 12. Times negative 2 is negative 24. Ooh. Okay, do you guys see what's going on the inside of that square root? I'm not going to get any real solutions from this. So that tells me that I'm not going to get any critical points from where the derivative equals 0. Okay, so let's look at where the derivative doesn't exist. So our derivative function is a polynomial. Polynomials don't have any discontinuities. So that tells me that this is not going to have any critical points from where the derivative doesn't exist either. All right, so when we make our number line, we're supposed to put any functional discontinuities and then any critical points on there. We don't have any of that. My function is continuous everywhere, and we don't have any critical points. So I'm still going to write up my number line, but I'm not going to have any x values to put on it. So what in the world am I going to do? It's fine. You can literally plug any number from the functions domain into the derivative. They are all going to have the same derivative values. So I'm going to plug in 1. Typically my go-to would be 0, but if I plug 0 into my, oh, actually I can do that. Let's plug 0 in. I just get -1. So that tells me that my function is going to be monotonic decreasing because my derivatives are always going to be negative or 0. I'm going to say f prime, or f of x, not f prime, is monotonic decreasing because f prime of x is less than or equal to 0 for all x in the domain of f. Okay, let's move on to page 3, which houses example 4. Part A says, suppose the provided graph represents f of x. Identify where f is increasing and where f is decreasing. I would also like to point out that this graph is continuing on forever. I just can't put arrows on a Desmos graph without doing that, without a lot of extra work. So go ahead and write that up. All right, so my graph is increasing on the right side if this is f of x, and it would be decreasing on the left side. So it's increasing from this x value is 0. We don't include the turning point to infinity, and it's decreasing from negative infinity to 0. In part B, let's suppose that this graph represents f prime. Where would our function be increasing versus decreasing? Remember, graph is going to be increasing where the derivative is positive, and then it'll be decreasing where the derivative is negative. Go ahead and figure out those intervals. Okay, so if this is literally the derivative graph, if I want to find where the derivatives are positive, I'm literally just looking at where this has positive outputs. So my graph would be increasing from negative infinity to, negative 2. And then again from 2 to infinity, because those are where my f prime outputs are positive. For decreasing, that would be where my derivative is negative, or where my f prime outputs are negative. So from negative 2 to 2. So if I have a f graph, I can look at that one of two ways. I could look at where is my graph going up versus down. Or I can look at my slopes. If I have my derivative graph, I need to look at my derivative outputs. And that is it for this set of notes. If you have any questions, make sure that you ask.